Hello everybody, thank you for coming to this session on robust and far-field speech recognition. My name is Alessio Brutti and I'm co-chairing with Richard Stern, who was very kind to wake up in the middle of the night and co-chair from remote.
Yes, thank you. I am so sorry to not be able to be here in person. I had every intention and every plan. My flight got canceled about 5 days ago, just before I was about to go, and it was simply not possible for me to get an alternative, all COVID-related problems. So it's a pleasure to be here virtually. In any case, Alessio Brutti from Trento and Verona will begin with the introduction to the session.
Okay. Thank you, Richard. So I think we have a quite busy session with 5 papers. 4 are here and 1 is from, could not make it, so we have a video. So I think we can start with the first one, the presentation. Oops, sorry. I don't know, I made a mistake here. So the speaker is Gong, and he will present this work titled Self-Attention Channel Combinator Frontend for End-to-End Multi-Channel Far-Field ASR. So, Gong,
hello,
the floor is yours.
Everyone, I'm Gong. I'm from the Nuance communication from Austria. And I'm a person who started, so if I have the repetition or some block during the speech, don't be scared. This research is carried out under the context of the medical conversational speech recognition. So where you can see that this is a typical clinic room that we have probably multiple speakers inside that, where you can see there's a patient and the doctor, but it could include some other speaker here. And inside this room, and we can also see there's a linear microphone array that is mounted on the wall. And you can see from this lower picture that this is this microphone array prototype that we used to capture this audio inside the room. And in this work, we're only using the 8 microphones, the left part in this array. And the inter-microphone distance is 33 milliseconds. And when we have the audio captured, then we send into this ASR system that with a multi-channel front end. And the output is the transcription. And in this work, we explore the cascaded multi-channel ASR system. What does it mean? That means we put on top of the single channel input ASR with a multi-channel front end. So the input to this multi-channel front end is the multi-channel audio. That why we choose to using this system, because it gives the flexibility to pre-train the front end or the back end. So especially if we have a lot of single channel training data, that we could pre-train this ASR and then put the front end to do some adaptation. And also there's a lot of choice for designing this front end. For example, we can using some classical signal processing approach, or we can using some neural networks there. So in here, just list some typical front-end design. For example, the most common one is we could using this delay and sound, or we could using the MVDR, which is also implemented in this ESP-net. And also we could using the spatial filtering that learns different fixed beamformers that in different steering directions. And then you can choose to one these filtered directional signals, or you can do combination. And in this work, we propose to use in the self-attention channel combinator, in short, SACC. So this is the topology of this front end. Actually, this kind of front end is also called channel-wise attention, and it has been used for the speech enhancement work. And in this research state that we're only using this SDFT magnitude as the input. And the output here is the single channel representation. So, and when we got the input, we put through 3 dense layers to generate the query key and the value. And once we get these 3 values, we can calculate these attention weights. And after that, we multiply these attention weights with the value that we could get this channel combinator weights. And then we multiply this channel combinator weights with the original input and doing this weighted sum. And then we can output this single channel representation. So this just to illustrate this difference of the self-attention that applied in this SACC front end and in the transformer. And in the transformer, as we can see, this query key and value are typically single channel time frequency representations. And the attention weights is computed on the time dimensions. For example, after we using the query and keys to compute the attention weights, and these dimensions here, we see it's on the time frames. And after that, we multiply these attention weights with the value, we can get a new speech representation here. But in SACC, this query and key is actually the channel frequency representation. So before we calculate the attention weights, we're doing this permutation. So as you can see here, the attention weights is the channel plus channel. And here the value is actually a vector, and we set here the feature dimension equals to 1. And we can multiply the attention weights with the value to get the combination weights. So, and this table, we want to show the difference between this SACC front end with the beamforming. And in SACC, we don't using the phase information in this research stage, but in a beamformer that we have to use in the phase information. And in SACC, we estimate this combinator weights on the frame level. But in this beamformer weights, it's usually estimated for the whole utterance. At least this is the implementation in the ESP.NET. And the third one is in SACC that we applied these weights for all frequency beams. But in this beamforming, it's usually the narrow band, so which means you estimate these beamforming weights per frequency. So next one, we talk about the experiments. So the first thing is the ASR system we use for the experiments. So here we're using this attention-based encoder and decoder ASR. And as you see, we have the front end here. And for training, we're using the spec augment. And the encoder, we choose a variant of ContextNet. And the decoder is just a single layer LSTM. And we using this cross entropy loss to do the optimization. And for the training and testing data, the training data, we're using a 460 hours. We choose from the Libli speech and the Mozilla Common Voice data sets. And we're using some criterion, for example, C50 SNR and PASC to select the clean speech from them. And to generate the multi-channel audios that we convolve the single channel clean data with the 8-channel room impulse response. And after that, we add some ambient and bubble and fan noises, yeah. And for the testing data, that is also simulated, and we're using this Libli speech test set, but we record it in this clinic room, and we put 4 loudspeakers inside the room, and here you see these positions. And this loudspeaker is actually the artificial mouse. And as you can see, there's also linear array that is mounted here. And during this recording session, those artificial mouths are static. And also there's some typical furnitures inside the room. And there's a standard office the noise sources. And for experiment, we're choosing the 4 baseline to compare with our SACC front end. The first one is the SDM, it's a single distance microphone that we always choosing the 5th microphone from the array for training and for testing. And the second one is the random channel, which means we randomly choosing the channels for the training, but for testing, we always choosing the 5th one. And the third one is the MVDR beamformer, but this one just separately is not jointly trained with the ASR. And the 5th one is the spatial filtering beamformer that we learned the ways for 11 fixed beam directions. And this one is jointly trained with the ASR. And the last one is our proposed SACC that we're using 3 fully connected neural network, which the dimension is 256. And here it shows the result here. And you see this proposed system is better performing than the others. And another observation you can see is this random channel microphone is performs almost equally than this MVDR beamforming. And we think it's because it's kind of a data augmentation strategy, because during the training, this ASR model could see more different channels. And the last 2 slides just to show what this neural network learns. And the first one is actually to show this attention weights. So the attention weights is actually the inner product between the query and key. So it could be interpreted as the similarity between this query and key for each channel pairs. So here is the this attention weights matrix for one utterance. So we have set this diagonal to 0 because these values are quite large. So from this attention weights matrix, we can see the query in channel 3 is quite similar to the key in channel 4. And as well, we can see the channel 6 of the query is quite similar to channel 7. And the last slides, I want to show you what this combinator weights it has learned. So actually, these are the same playback speech playback audio, but it's playbacked in 2 positions in the room. So where you can see the first one, we see the channel 3 have the largest weights, but the channel 7 and channel 8 has the lowest weights. Why are we changing these positions? We can see in this one, the channel 1 have the lowest weights. Yeah, so that's all my presentation.
So thank you very much, Rong. We have time for some questions, either from the audience or online. Sanjeev, the microphone is.
Thank you, Rong. A couple of years ago in the Chime Challenge, the Paderborn guys got some pretty good results by using this guided source separation. So they were using speaker information to sort of, do the beamforming. Did you look into anything like that? Do you have a sense for whether that will be useful in this setting?
No, we haven't explored this speaker to using speaker information. But if you can elaborate it more, for example, how it's using it.
The paper is by the Paderborn group. Reinhold might be here. I don't know if I see him. But it's called guided source separation.
Okay.
So, I mean, they do have beamforming, but what they do is they use an initial pass of diarization to figure out where the speakers are, where they might overlap, and so on and so forth.
Okay.
And it is doing
yeah.
Okay.
But in our use cases that we don't have too much these overlapping speakers, so it
Just to know, it just gave them very
okay.
results.
Yeah. Thanks.
Okay, there is one raised hand. I try to invite him. I don't know. Okay. Rui Chenlin, let's see if picks up. It's not picking up. Okay, there is one question online from Andreas Schwartz, Amazon Alexa. So I'm reading it. Thank you for the presentation. I'm surprised by the large improvement you are seeing since you seem to be not making use of phase information, which has most of the spatial information in a closely spaced microphone array. How do you explain the improvements?
Okay, so I think because this the microphone array dimensions is not large. If you think there's 8 microphones in that, so the largest distance you have the 7 microphone distance there. So the largest sample shift it could be is probably like 10 samples. So I guess in this case, the phase information is not important because within this kind of SACC frontend, you just choosing the these microphones with the best speech the best speech quality, yeah.
Okay, thank you. So the raised hand is not picking up. Are there other questions from the audience? Okay.
Okay, so we should move on to the second paper.
Now we have a question from the audience.
Yep.
So on the last slide, you were showing which of the microphones were used. I don't know if you can quickly show it or not, but it said in the caption, moving average. Is that what you actually use as well, the moving average, or was this just to display?
The moving average is just for the visualization, because if you don't do that, this figure will be quite noisy.
Yeah. Okay, and that's actually the reason why I'm asking. Doesn't the ASR get confused quite a lot if you keep jumping from microphone to microphone all the time, if that's like very jumpy?
Yeah, so maybe, but I mean, it could be like confused, or it's jumps as per frame is also time varying, right? It's probably just to, for each frame is try to select, for example, which microphone is the best one.
Yeah, I'm surprised it works that well if it's so discontinuous, but apparently it does.
Yeah.
Okay, thank you.
Okay, thank you.
Okay, thank you very much. So let's thank the speaker again.